In chapter 11, we're going to talk about inferences for population and standard deviations. There are two sections in this chapter, but we're only going to cover section 11.1, just one section. And that section on inferences for one population standard deviation, sigma. Remember, when we talk about inferences, that means we're talking about generalization to the population parameters. We've done that for the mean in chapters 8 and 9 and 10, which in fact in chapter 10 we inferred to two population means. And we also did it in chapter 16 to multiple populations, means of course. So in chapter 11 we want to do the same thing. That is, we want to do point estimation, confidence intervals, and hypothesis tests about sigma, the population standard deviation. So we're going to begin with talking about this chi-square distribution. Notice please the pronunciation, CHI. I know it seems like, and it may even be tempting to pronounce this as chi, but the correct pronunciation is chi-square distribution. This chi-square distribution is going to be the fourth and the last of our probability distributions we discuss in this course. The distribution is continuous, as you can see from this figure 11.1. The distribution is continuous. So being continuous, that means areas are probabilities. So to find probability of a random variable lying between two values, we need to find the area under the curve. Now the author does give us a table in the back of the book, but I'm not even going to go into that table. We simply rely on StatCrunch either to obtain the area under the curve or answer probability questions, or to actually do our inferential work. But these are some of the characteristics of this chi-square curve. The first property, again, total area is 1 because this is a probability distribution. The area under the curve has to be 1, meaning 100%. The chi-square, unlike the normal and t-distribution, the chi-square, just like the f distribution we saw in chapter 16 when we talked about ANOVAs, starts at 0. Okay, so there are no negative chi-square values. All chi-square values are positive. Now, something that's interesting about this curve, the parameter, that means the unknown of this distribution, is going to be its degrees of freedom, just like the t was. This is a mathematical curve, so it does have a very complicated mathematical expression for it. You can Google it and see the expression for yourself. I just didn't want to overwhelm you with it. But anyhow, it does have a mathematical formula for it. So one thing that's interesting is for low degrees of freedom, let's say 3, 4, 5, and so on, this distribution is peaked and severely skewed to the right. As the degrees of freedom increases, you can see it goes from 5 to 10 to 19. The distribution becomes more and more, it takes on the form of a normal distribution. In fact, for very large degrees of freedom, the distribution approaches normality. Something that's very common with chi-square values, you can see these scores, see how high they are, how large they are. So it is not unlikely to see large chi-square values. And remember, because of the asymmetry of the distribution, we can no longer reflect, for example, from the right to get the values that are in the left tail of the distribution. Okay, and a couple of interesting factoids about this distribution is that the mean or expected value of the random variable that follows a chi-square distribution, the center of this distribution is the same as its degrees of freedom. So if you look at, for example, degrees of freedom 19, right about here, that's where the the center of this distribution or the mean is going to be. And again, this is right about here-ish there. For the one with 10 degrees of freedom, of course, that's the center of that distribution. 5 degrees of freedom, that would be the center of that distribution. Okay, so just want to point that out. And then the variance is twice the degrees of freedom. That's what the variance is, twice degrees of freedom. We're not going to directly work with these, by the way, the mean and variances. That's just kind of general information. Now, being a continuous distribution, again, we're interested in finding the area under the curve. And I have one thing written up here, just again, another interesting idea or fact about the distribution. This distribution was actually discovered by Helmert, the German statistician, and particularly in Germany, naturally. They know this as a Helmertian distribution, but the distribution was rediscovered by Professor Carl Pearson as he was doing work on chi-square goodness of fit test. Now that chi-square goodness of fit test, by the way, that I just pointed out, it is in chapter 13 of this book, but we're not going to cover that chapter. If you're interested, you're free to read through that chapter and find out about that test. Okay, so let's take a look at actually how we're going to find the area under these curves. So here's an example in the book. Okay, so we're given a chi-square curve with 12 degrees of freedom. And in the left, part A, we want to find the chi-square value. So the area to the right is 0.025. Now remember the notation, the subscript notation here in this case, 0.025. That means we want to find the area to the right to be 0.025. So that's what the subscript means. So here's the value he gets from the table. And the area to the right is 0.025. And he does point that out in the writing that I believe is table 4 or something like that. But again, we're going to use a StatCrunch. In a moment, I'll show you these numbers. And we'll go to StatCrunch together and actually see how this is done. And here's a second example. So in the second example, again, this time we want the chi-square value, so the area to the left. Notice the area to the left is 0.5. And this one is 7 degrees of freedom. So again, how do you go to do this? He goes to the table in the back of the book. And actually, if you see his table, again, I don't show it because we're going to use StatCrunch. But in his table, he always give area to the right. So he actually will not have an 0.5 on the left. In this case, he's going to look at 0.95 to the right. But however he does it, doesn't matter. We get these numbers in a minute. The chi-square, so that area to the left is 0.5. That's going to be 2.167. Notice there's no subscript on this chi-square as there was one with this one, because that's the right tail, so that he uses a subscript. If he was to use a subscript on this one, by the way, he would have to use a chi-squared with subscript 0.95, actually. That's what it would have to be. 0.95, because remember, the subscript always tells us area to the right. So this would be written like this. It's going to be a chi-squared 0.95. That's what he could have done here. But he chose to just write it as chi-squared. Okay. So let's see. These numbers, the numbers that we have. Again, I'm going to make a note of these because when we go to StatCrunch, I'm going to have to remember these numbers. And degrees of freedom, for example, number 2 is 7. And the area to the left, 0.5 left. Okay, we'll do that in a minute. But I've already done it. I just want to show you what the StatCrunch work looks like. So here's for the first example. Example 11.1. Okay, remember his number here, 23.37. And check this out. That's this output. So in StatCrunch, degrees of freedom is 12. Greater than or equal means right tail. And I typed in 0.025 here, and this is what came out, 23.36664, and so on. Remember, StatCrunch gives us more decimal than his table scores go for obvious reason, because the table has a limitation, page limitation, so it's got to keep it concise. For example number 2, we want left area to be 0.05. Notice in StatCrunch, I can actually go left area. So the adjustment here, sorry about that, the adjustment that you make here is the following. So if you want the right tail area, greater than or equal. If you want left tail, you go less than or equal. That's the adjustment you make here. Greater than or equal, less than or equal. Then again, I typed in degrees of freedom, 0.5, and this is what came out, which is exactly the same number as you see up here. Okay. And there you go. So let's actually go to StatCrunch now and see how these are done. So I have already StatCrunch up and running. And in StatCrunch, there it is. Don't worry about this data. We'll look at this data later on. But here, to get the area under the curve. So we're going to go to Stat. You then go to Calculators. And then here's a roster of all these distributions. Right up here, the third choice, that's chi-square distribution. And you click on the chi-square distribution, and there you go. This is what pops up. Default degrees of freedom 10. We don't need that. So to do his first example, the one that had 12 degrees of freedom. Okay, so I'm just going to type in 12 here. And we wanted the area to the right, so I'm going to go greater than or equal. And the area to the right, we wanted it to be 0.025. Okay, so there you go. Degrees of freedom, right tail, and this is the probability. Compute, and there you go. That's how we got that one. Again, pretty easy, straightforward, simple to do. Let's do the second example. In that second example, I'm going to go Stat, Calculators, chi-square. And for this one, degrees of freedom was 7. So I'm going to type 7 degrees of freedom. And we want to keep that as less than or equal. Remember, less than means left tail. That's the direction for the probability. And 0.05 is the area we wanted on the left. So we're going to see a shaded region on the left side in red. And there you go. The area to the left of that is 2.1673. Now, one thing while I'm here, let me show you. Again, this is because in the exercises, we'll see this in a moment. So 5% area to the left is the same as 95% to the right, correct? Of 2.167. At that point, at 2.167, area to the left is 0.05. That means the area to the right must be 1 minus that. 0.95, correct? So check this out. I'm going to change that to greater than or equal, and there's 0.95. It's important when we look at the formula for confidence interval, the notation that you will see, and again, in a few minutes, you will see what I mean, but the reason I'm showing this is because of that notation that shows 0.95 to the right. So remember, 0.95 to the right would be the same as 0.5 on the left side. So here's, again, let me go back to my notebook. So this is how I got these numbers. Okay. Now, let's take a look at another example. In this example that's in the book again, what he's doing, he wants to find two chi-square values this time, so that the area to the left is 0.25, to the right is 0.25, and again, note that there's no symmetry here. So we cannot use the center line symmetry and reflect right, left tails in order to get these values. Now, 5% total shaded area, right? 2.5 on the right, 2.5 on the left. That means you have 95% between. And again, from his table, he gets these numbers. So we want to get these numbers again ourselves. Remember, we want 0.25 on the left, 0.25 on the right. Degrees of freedom is 20, 95% in the middle. Okay, so I did, and there you go. The key is when we go to StatCrunch to find the area under the curve, that this time we actually use the option between. Okay, and that I have it here circled in green. Now I'm highlighting it in yellow. That's the option that will give you the between areas. And this is actually a clever way of doing what he has done in order to get these two extreme numbers. For the right tail, 34.7 is right here, and for the left tail, 9.591 is right here. Okay. So that's how I would find these values. Again, we need this in order to do our confidence intervals later on in the section. Okay, and maybe I'll go to StatCrunch and show you this again. 20 degrees of freedom, and let me change that to 20 degrees of freedom. And I'm going to go between, and to the right here, type in between. I want it to be 0.95. Remember, between 0.95 means 0.25 on either side. And there you go. So those are the numbers that you saw earlier in my output right here. Okay, so we're done with his examples. Now let's take a look at the exercise ourselves. So we're going to do this ourselves now. This exercise number 6, we'll look at a couple of exercises in this segment. For a chi-square curve with 22 degrees of freedom, find chi-square value that has an area 0.1 to its right and 0.995 to its right. You see, this is what I was talking about earlier when we did 0.5 on the left, and I said that means 0.95 to the right because of kind of exercises that you see here. So with 0.995 to its right, that means 0.005 to the left, right? Okay, so 22 degrees of freedom, and this is what I've done. Again, I just went to the chi-square option in StatCrunch, and that's how I got these numbers. So part A, 0.1 to the right, that's 0.1 to the right. 22 degrees of freedom, that's that. I typed in 22, put in 0.1 to the right, and make sure this is greater than, means right tail. And here's the answer, 40. Note how large that number is, by the way, 40. That's just the nature of chi-squared. The bigger the degrees of freedom here is, the more likely to get high scores. So if I have 2,000 degrees of freedom, then my values will be in the order of 2,000 to 3,000, 4,000, things like that. Although we will not work with things like that. Okay, the middle one, this one is, now I'm doing 0.995 to the right. I'm actually using 0.05 on the left. You see that? Less than 0.05 on the left. And that number is 8.642. Or you could have done it this way. You could have done it this way. You go to the right and actually type in 0.995 to the right. And you get the exact same number. You see that? The scores are the same here. So that's how you do this. Pretty easy with StatCrunch, isn't it? In exercise 11.7, he's doing the same thing he did in in exercise number 6. The difference is that now he's using the chi-square, the subscript notation. So this is chi-square, Greek chi. Looks like italicized x. So this is chi-squared 0.5, means we want to find the chi-square with 10 degrees of freedom, so the area to its right is 0.5. In part B, the area to the right is 0.975. Remember, subscript means right. Right 0.5, right 0.975. And you can verify these now yourself using StatCrunch. So I put 0.05, 10 degrees of freedom, 0.5 to the right. That's the answer. And if I want in part B to do 0.975 to the right, you can just type 0.975 greater than to the right, which means the same as 0.025 to the left, less than. And again, you get the same scores. So those are the answers to this exercise. Now, let's actually begin with what we want to do here. So in this chapter, we actually want to draw inferences about sigma, the population standard deviation. But we're going to be using actually the theory, the distribution theory that follows for the variance, the population variance. Okay, so keep that in mind. And the reason, the short reason or excuse for doing this is because the sampling distribution, that's what we need. We need to find the probability distribution of the point estimator of sigma. And you will see in a moment, the trouble is going to be with when we try to find the probability distribution of a sample standard deviation, which becomes the point estimate of population standard deviation. that sampling distribution does not have a closed form. Its distribution is unknown. Okay, so for that reason. So one thing I just want to recall here is the relationship that's between variance and the standard deviation. We're going to tap into that relationship between them and actually indirectly construct confidence interval and test hypothesis test about standard deviation through variance. Okay, that's a pretty clever way of doing it. Now, the sampling distribution theory, I mentioned that is going to be based on the variance, and once we draw inferences to variance, we can relatively easily make adjustments or adjust those findings for population deviation. So here's our first work toward estimating population deviation sigma, our first of 3 inferences. All our inferences are in 3 categories: point estimation, confidence interval, and hypothesis testing. So our point estimate of sigma is going to be S. That means the sample standard deviation. So that's pretty simple, common sense, right? If you want to know what the deviation in the population is, why don't you look at the deviation in the sample? Now this S, by the way, in chapter 3, we looked at sample standard deviation S in chapter 3, right? Now, here is where we're kind of going to switch the theoretical work that follows. This is where we make a switch from S to S squared now. So instead of working with sigma now, from here on out, we're actually looking at sigma squared. So, and the reason, again, it turns out, I have it written here for you, the sample standard deviation is not going to be an unbiased estimator of population deviation. Okay, and that's not a good thing. We would like to have unbiased estimators. Therefore, for that reason, the sampling distribution of S isn't used to test hypotheses and construct confidence intervals. And by the way, even if we want to do that, you say, well, I don't want biased estimators, give me that sampling distribution. We wouldn't be able to do that because it doesn't have, again, a nice closed form like we have in all other instances we had so far. We had to resort to simulations and generate these sampling distributions by taking repeated samples and so on and so forth. So, which would be beyond our reach for this course. So instead, what are we going to do? We're going to use the probability distribution, the sampling distribution of a multiple, not even S squared, a multiple of S squared, which is the sample variance. Okay, and you'll see what that multiple or scaled version is in a moment. Now, here from now on, remember we're talking about sigma squared. We're going to put sigma aside. So S squared turns out to be an unbiased, and not only unbiased, but it has an extra additional interesting attribute that it is minimum variance among all other estimators of sigma squared. So we use sample variance for that reason. It's not only unbiased, but it has low variation. So that's what that is. Now, I'm going to give you something. See, I have it. It's not in your book, but this is for those that are really interested and they may, for one reason or another, choose to become statisticians. And it's just some people are interested in the mathematics of what we do. After all, this is a math course, right? It's just we're not doing the detailed mathematical work. We just throw in formulas at you. But there is a reason for every formula, and where do they come up with it? So here's one thing I want to show you, because in the book, the author, you will see part of this in the book, okay? It's not the way I'm stating it here, though. I'll show you the part that's in your book. So there is this important theorem called Cochrane theorem, which gives us the sampling distribution of S squared. Okay, so that theorem says that the sampling distribution, the probability distribution of the sample variance S squared, follows a scaled, not quite chi-square distribution itself, but a multiple of a chi-squared. And I have that down here for you, right in here. That's what the multiple of a chi is. This is a chi-squared. Now, of course, the degrees of freedom here is going to be n minus 1. Okay, that's what this notation is. So here I'm using a subscript for degrees of freedom. It's not the area to the right. Okay, that means sample size minus 1. Usually, for chi-square curves, we put degrees of freedom as a subscript. Some do, others don't. I do. So, its sampling distribution is going to be chi-squared. Now, the center of this sampling distribution of this multiple of a chi-square, the center of it would be sigma squared. See, that's what it makes S squared an unbiased estimate, because the mean of the sampling distribution, the center of the sampling distribution, is sigma squared, the parameter we want to estimate. And the variance of it is given by 2 sigma to the 4th over n minus 1. And this is, of course, assuming that we're drawing observations from a normal distribution. Okay. Now, what if we're not sampling from a normal distribution? The formula actually for the variance is going to be different, but not for the mean. It's just the variance is going to be much different. Okay, so there you go. That's what that is. Now, because we have the sampling distribution of S squared, right, we will be able to, or a multiple, I should say, of that, we should be able to draw inferences about sigma squared. And this is where now we're getting into what is in your textbook. So again, to recap, a point estimator, an unbiased point estimator of sigma squared is S squared, the sample variance. That means the expectation, E here stands for expected value or expectation. The expected value of S squared is going to be sigma squared. That's what unbiasedness means. Now, we have a couple of assumptions here before you see this formula. One is the usual assumption. We have simple random sample with replacement from a finite population, or without replacement from a very, very large population. We're removing items. A few items from it are not going to change the probability distribution or probability of subsequent selections. And the second assumption is the normality of the population. Now, this assumption is really important because what we're about to do, this formula we're about to see, is very sensitive to departure from normality. So usually what we do is we do like maybe a QQ plot or a box plot of the sample data, and we can assess the normality visually that way. And of course, there are actually analytical methods that test for normality. But anyway, just got to be careful when you use this. So let's do our things. So what we're doing now, we want to do hypothesis tests and confidence intervals, and that's what we want to do. And here come the formulas. And there you go. This is the formula that's in your book. But hopefully now you see the reason for this formula. The reason for it is up here, right under what's not in your book. See right in here. The reason for it is this statement right in here. In this statement, by the way, if you multiply both sides by n minus 1 divided by sigma squared, multiply by n minus 1, both sides, you lose it here. You have n minus 1 here. Divided by sigma squared here, so you don't have anything left. And you get the chi-squared, which is exactly what the author has. There you go. Okay. Now, we want to test the hypothesis about the standard deviation. See, this is what we wanted to do, but we're not going to actually do this. We're going to go through this. Remember, sigma, you square it, becomes sigma squared. The sigma with a null symbol, sigma naught, they call it. And the naught here, let me write it here for you. I'm writing this. It's going to be, sorry, my pen is not cooperating with me nowadays. Okay, sigma naught. That's the kind of naught. It's like naughty. So this is sigma naught. Okay. Sigma naught is what we call the hypothesized value of the standard deviation. So to test this hypothesis is to test this hypothesis because we know now the sampling distribution, right? So our test statistic is going to be this: degrees of freedom n minus 1. And our decision is just like before. We're going to reject if p-value is less than or equal to alpha using p-value criterion, or if we go off of the critical value approach to hypothesis testing, we're going to reject if our test statistic falls in a rejection region, right? For the left tail test, if we fall in the left tail; for the right tail test, if we fall in the right tail; for two tail tests, if we fall into either tails, we're going to reject the null hypothesis. There you go. The formula is actually pretty simple. Now, how about confidence interval? To construct confidence interval for sigma squared or sigma, you have the formulas. The theory actually is established for sigma squared. This comes first. So the lower limit of the confidence interval is given by n minus 1 s squared over the chi-square value. It looks almost like your test statistic, except down here. Okay, and notice when you swap out sigma naught squared and chi-squared, put it here, you solve for sigma naught squared. That's what this becomes. So this is the lower limit, this is the upper limit, and look at the subscript. We're back to subscript alpha over 2, means area to the right is alpha over 2. And this would be chi-squared 1 minus alpha over 2. Again, the area to the right would be 1 minus alpha over 2, which means the left area is alpha over 2. Now, to convert this into a confidence interval for standard deviation, because sigma is the square root of sigma squared, right? Standard deviation is when you take the square root of the variance. So from this, we get a similar formula with the square roots. Okay. And there you go. Now we can do our exercise. So again, to recap, we have two important formulas. This is really all the author talks about. He gives you the test statistic, just like that, for the hypothesis test, and he gives you this. Those are the two formulas we have. One up here, one down here. Okay. So let's take a look at this, and the work that we do in this section, by the way, you can do the whole thing in StatCrunch. So in this exercise, I want to do number 16. In exercise number 16, up here in blue, it reads, we have provided a sample standard deviation and sample size. In each case, use the one standard deviation chi-square test and the one standard deviation chi-squared interval procedure to conduct the required hypothesis test and obtain the specified confidence interval. So number 15, you might want to try that once we're done with number 16. So in number 16, I've written the specifics here for you. We want to test the hypothesis that sigma, notice we're testing hypothesis about sigma, but all our theoretical work is off of sigma squared. We want to test the hypothesis sigma is 4 against the one-sided alternative, left-tailed, sigma less than 4. Our significance level for the test, the size of our test, alpha is 0.5. The sample size is 10, and the sample standard deviation is 2 in this case. Okay. Now, here's our test statistic. Pretty simple. It's just a ratio of two numbers, right? And everything is given to us. Sample size was 10, so that goes in here, 10 minus 1. Standard deviation was 2, that becomes the squared, 2 squared 4. And notice this is sigma naught squared, means variance. We're given deviation, so you square 4, you get 16. And this is 9 times 4, 36 divided by 16, and I got 2 1/4. Excuse me. 2 1/4 is what I got. So, and here's StatCrunch. Okay. Now, one thing right off the bat, let me explain before I forget here. If you look at the output from StatCrunch, remember, we want to test the hypothesis. Let me do it here. That this is 4, right? The deviation is 4. But look at this. You don't see 4 here. You see 16, right? Because StatCrunch does this for variances. So you got to be very careful. And I'll emphasize, and again, I will reiterate this when we go to StatCrunch. StatCrunch works with variances. The exercises work with either variances or standard deviations. So you got to be really careful with that. But there you go. Just to point out again here, that 2.25 is exactly what this is. So we got the same thing. So this is your test statistic. And the p-value, don't worry, we just rely on the software. I'm not going to show you where that came from. And here, the usual procedure is p-value is less than 0.05. Yes, it is. So we're going to reject the null hypothesis. That means the deviation alternative prevails. That means deviation in the population is probably less than 4. And you can see that. Look at the sample deviation and look at the hypothesized deviation. They're pretty different, aren't they? They're quite different. Standard deviation is half that of what the population claims it to be. Okay. All right. So just wanted to point that out. And let me clear these up. Now, what if I want to do this by critical value approach? And again, I'll show you where to do this in StatCrunch in a minute. The other approach, critical value, the reason I mention critical value, by the way, it's like, well, if I can do it this way, why do I want to do critical value? It's because I believe in my math lab, in the questions, the exercises you do, it will ask for critical values, especially on the exam. It will ask for critical values. So that's why I want to do it, so you kind of see how that is done. Okay, so let's take a look at this one. So remember, to be able to find the critical value, we need two pieces of information. We need the significance level alpha, and we need to have the alternative, whether it's less than, greater than, or not equal to. Those two pieces of information is what we need here. Okay, so I went to StatCrunch. Remember, alpha is 0.5 and less than means left tail. We want that to be 0.5. Critical value is this value, the value that separates your rejection, that's region in red, the rejection region, from the clear region, the non-rejection region. And that's the cutoff point. So I went to StatCrunch, and you know how to get these areas now, right? I went to degrees of freedom. I plugged in a 9. Remember, sample size was 10. 10 minus 1 was 9. Left tail, because this is less than. And I put the size of our test, 0.5, in here, and that's our critical value right in here. Using critical value approach, remember our test statistic from above was 2.25 is right here. 2.25. 2.25 is less than 3.325. That means we are in that rejection region. So we're going to reject the null hypothesis. So we've done it both ways now, using critical value and using p-value. Now, let me again continue on with this. And once we do confidence interval, then I'll go to StatCrunch. So in part B of that exercise, 90% confidence interval, right? Number 16, 90% confidence interval. So for this one, I just plug in the numbers into the formula. For 90% confidence interval, that means alpha is 10%, half that 5%. The 1 minus alpha over 2 would be 0.95%. So we need those down here. And there you go, just to show you. See down here, the lower limit is chi-squared subscript alpha over 2. That means chi-squared 0.5. From StatCrunch, I got this. And then 1 minus alpha over 2, that's 1 minus 0.05. It makes it 0.95. Again, from StatCrunch, I did the left tail 0.5. or the right tail 0.95. And I got 3.325, both of those numbers, and I plug them in. Sample size 10, sample deviation was 2. So the numerators are identical, it's just the denominators are different. So the lower number, which is 3.325, right, that goes with this one. The higher number goes with 0.5. And you plug it in and using a calculator, this is what I got. I got 1.46 to 3.29. So we're 90% confident that the population deviation lies somewhere between about 1.5 to a little over 3.3, call it. Now check this out. When you run StatCrunch, remember StatCrunch does variances. They don't do standard deviation in this section. So look at the confidence interval. The confidence interval I got from StatCrunch, the lower limit is 2.213, call it. Okay, and check this out. This number, oops, sorry. Let's say, there you go. Look at these two. The upper limit is 10.8. We have 3.29. They are not the same. The reason, this is confidence interval. In StatCrunch, they gave us confidence interval for variance, not deviation. So what are we going to do? Well, using the relationship between variance and deviation, I know if I take square root of these numbers, they become deviations, right? So I did. If you take square root of the lower limit, that 2 point whatever here, you get 1.46, and then take the square root of the upper limit for the variance, you get the upper limit of deviation. So that's how we're going to get around it. You got to remember this one, folks, because again, on your homework and on the exam, this is how it's going to be. All right. And I have it as a note for you here. I'm hoping you can again pay attention to this part. This is an important note we have. StatCrunch does inferences for the variance. Okay, not standard deviation. All right, now what I've done here, let's actually go back and do these outputs that I got for hypothesis and confidence intervals. Let's do these from StatCrunch. Okay, so again, the alternative here is sigma is less than 4 and our alpha is 0.5. Okay, and our confidence interval 90%. I'm looking at the statement of the problem here. The sample size was 10 in this exercise and sample deviation was 2. So we're going to go to StatCrunch. And here's where we're going to go to a place we haven't gone before. So we go to Stat, and then we go down the list, and you see that the variance, not standard deviation. So we go to Variance Stats, and then we only have one sample. In Chapter 11, Section 2 deals with 2 samples. I just want to do one sample here. So this is all you need from this chapter. Now we're going to go with summary. In exercise 16, they gave us the summary. Notice how simple this interface, the pop-up is. It's asking what is the sample variance. And remember, in the exercise, we had the sample deviation. That was given to us to be 2. So I need to square that 2, it becomes 4. Okay. Our sample size was 10. And that's it. Now, the hypothesis test for, here's where you got to be careful again. It's asking you, what is the hypothesized variance? Remember, in the exercise, it was 4. I need to square that. Type in 16. And we were doing a left tail test, less than. And this is where the confidence interval would be. You can only choose one of these radio buttons at any time. You see that? When I choose this, the other one goes away. When I select this one, the other one is deselected. And then compute, and you'll see the familiar output. Again, this is what we got, right? Earlier, we saw that. Let me go Options, Edit. I'm going to change that hypothesis to a confidence interval, and we were doing what, a 90%. There you go. So it's again really simple. All you need is 2 pieces of information. What's the sample variance and what is the sample size? And here's compute, and there we got those numbers I had earlier. Okay, so hopefully that's easy to follow for you. Let me go back to my notebook, and let's see, the critical values, again, this you have to do it yourself. It's not something in the output that StatCrunch gives us. Okay, And that brings us to this exercise now. Okay. Now, in this exercise, it reads, gas mileage estimates for cars and light-duty trucks are determined and published by the U.S. Environmental Protection Agency, the EPA. According to the EPA, the mileage obtained by most drivers will be within plus or minus 15% of the EPA estimates. The mileage estimates given for one model is 23 miles per gallon. All right, that would be like the average mileage on the highway. If the EPA claim is true, the standard deviation should be about 15.15, right? Because that's what was said here, 15% of the estimate. 0.15 times 23 divided by 3, which is 1.15 miles, whatever. Don't worry about this part. So here's where actually what we want to do in here is follows from here on out. A random sample of 12 cars of this model yield the following highway mileage. So there you go. These are the mileages of 12 cars. They're all within about 23 and a half, whatever the average might be. At 5% significance level, do the data suggest the standard deviation of highway mileages for all cars of this model is different from 1.15. Notice, by the way, how inferential this statement is right in here. For all cars. From 12 cars, these 12 cars, they would like to infer or generalize to all cars of this model, however many thousands there might be. Okay, so I went ahead and wrote down the specific of this one. The null hypothesis says that everything is fine. They're within the EPA guidelines, right? The mileages. And the question actually it's asking is, can we conclude, or does the data suggest the standard deviation is different from? Well, different from means not equal to, right? If they're the same, it's equal. The null says no, it's the same. They're not different from the hypothesized value. The alternative says no, they're different from what they should be. Now remember, we're doing things for variances, right? So immediately I need to square that hypothesized deviation, turn it into a variance, 1.32225, because when we go to StatCrunch, that's what we're going to need. And I did, and there you go. So that's where the 1.3225 comes from. And I'll show you in a moment again how I got there. So remember, in this case, again, the alternative is not equal to. The sample size was 12, and the hypothesized value of the variance is 1.3225. So before I leave this page, this is our test statistic. And look at the p-value here. The p-value is very large, so it's not even close to 0.5, much higher. So we definitely fail to reject this null. We have absolutely no evidence against the null. And look at the standard deviation that you're given here, by the way, 1.071. 1.071. Now, when we run this, I'm going to run this in two ways. Because we have the data, I run it with data, and then another, we're going to run it with summary stats, meaning if I know standard deviation that I'm given. Okay. So, first, to finish this off, our conclusion is that the standard deviation is not different from 1.15. Okay, and then our critical value approach, remember, StatCrunch doesn't do critical value, so we need to do it on ourselves. And I need two pieces of information, my alpha and the alternative form, which is a not equal to. That gives me a two-tailed test. And there you have it. So my critical values, how did I get this again? When alpha is 0.5 and this is two-tailed, it means I want 0.25 on the right, 0.25 on the left. So I chose the option between, and I made between to be 0.95. And then here, degrees of freedom, 12 minus 1 is 11, sample size minus 1. So that's how I got these two. There are two critical values for the two-tailed test. That's how you get them. Again, on the exam, it may ask you for critical values, and this is how you get it. So our test statistic was 9.59. That was right up here. Because 9.59 is in neither rejection regions here, left or right tail, we failed to reject the null. Okay. Now, for confidence interval, 95% confidence interval, again, I did that one. And it turned out to be the lower limit is this, the upper limit is this one. Remember, these are for variances. We need to take the square root of them. Be careful, folks. And there you go. So the standard deviation in the population is somewhere between about 0.76 to 1.8. And note the hypothesized value this is for standard deviation. The hypothesized value of a standard deviation was right up here, 1.15. That 1.15 actually is inside of this interval, right? Right in here, 1.15 is in there. So we do not reject the null hypothesis. I could have done that using the confidence interval, but we got to make sure the alphas and the size of a test and the confidence level actually works together, and that this is a two-tailed test of hypothesis. Then we can do what I just did. Okay, so we get the same result. Now let me go to StatCrunch to do this, to get the output that we got. We're going to do confidence interval, and we're going to do the hypothesis tests. Okay, our confidence level was 95%, right? Okay, so I'm going to go to StatCrunch now, X out. Now, I already imported the data in there. How you do that is, again, you go to, here's the chapter menu. Let me click return to chapter menu. So this is what I get when I enter StatCrunch using data sets from the book in my MATLAB. I'm going to chapter 11. And here's a list of all the exercises that have data associated with them. In number 22, you click on number 22. This is what's going to come up. So let's test the hypothesis. I'm going to go stat, variance, stats for one sample. I'm going to go with summary. Okay, although I see the data, next I'm going to use the data option, but let's go with summary. Remember, this looks familiar. What is the sample variance? Well, remember the author gave us 1.071. So I need to square 1.071 squared. And I get this number. I get 1.147. 1.147. Again, that's when I square the sample deviation that the author gave us, the very last piece of information in the exercise. Our sample size was 12, right? And we want to test the hypothesis for variance. The variance was 1.3225. And this was a two-tailed test, right? Compute, and there you go. So this is how we get the numbers. That's using summary statistics. Test statistic is 9.54 and change. Now let me do exactly the same thing with data. So I go stat, variance stats, one sample with data. Click on the mileage, left click once, and that's all. Notice I don't have to give it the sample size or the deviation, because the StatCrunch can find it from that column of mileage, because it has the data at hand. I do need to put 1.3225 here still, and let's run this. And there you go. You get the exact same output. It was 9.54. It was the third decimal was different when I used the summary stats, but this is more accurate. So again, on the homework or exam, whichever you're given, if you're given sample standard deviation, use summary stats. If they don't give you that, they just give you the data, then use the data option. And that's it. Now for confidence interval, options, edit. I'm just going to change that to confidence interval, and I believe our confidence level was 95 for this. Compute, and exactly the numbers we got before. Remember, these are variances. These are limits on variance. We need to take the square root of these two numbers, this one and this one, in order to get the answer they're looking for. All right, so with that, we are done with this exercise. Again, hopefully you follow everything we did. A little bit of theoretical work right about up here, which isn't, I guess, that's not so bad. Right in here, the thing that was in your book. Again, don't worry about this part that's not in your book, as long as you follow the formulas in green. And there you go, for the green part. As long as you can do this, I'm happy with that. But if you needed a little more, you got a little more for that. So we are done with chapter 11. Okay, we're only going to do one section in chapter 11, and with this we are done in chapter 11 and with this lecture.